Here comes the problem statement. Our task is to design an inverting amplifier to amplify an input signal, which is a sine wave, by 10 times, with less than 5% tolerance. To design a subsystem successfully, the first thing we need to do is to translate the problem statement to design specifications. This is to help us understand the problem. Since there are maybe many prototype circuits available for the design problem, the second step is to choose and design a prototype circuit. And step number 3 is to analyze the design circuit to see if it meets the design specifications theoretically. And the last step is to build and test the circuit. In some cases, our first design may be not successful. We might need to go over steps 2 to 4 to adjust our design. So from this problem statement, we can derive the design specifications as follows. We want an inverting amplifier, and we know the input signal, and we also want to make sure that the magnitude of the circuit gain is 10 plus minus 5%. In this case, there's no question that we will use an inverting configuration as the prototype. This is one of the most basic formats of op-amp circuit. In the schematic, this is the input resistance and feedback resistance. Notice the feedback resistor is connected through the negative input terminal. So this configuration uses negative feedback to stabilize the voltage gain. Since this is one of the first op-amp circuits we've talked about, let's analyze the prototype together. There are two golden rules about negative feedback op-amp circuits. Assume the voltage across the positive and the negative input terminals are V plus and V minus respectively. Then the first golden rule says V plus is equal to V minus. The second rule is about the current. The current into the input terminals are IA and IB. Then both of the currents are equal to 0. Since the positive input terminal is grounded, V minus becomes 0. If the current across Ri is I1, we can write out I1 is equal to V input minus 0 divided by Ri. We can do something similar for I2, the current across the feedback resistance. Now, from the second golden rule, because IB is equal to 0, we have the relationship I1 is equal to I2 at negative input terminal, node A. Combine those two equations together, we can derive the relationship for the circuit gain, which is defined as the output over input is equal to negative RF over RI. If we use 100 kilo for the feedback resistance and 10 kilo for the input resistance, we'll get a theoretical value for the circuit gain is equal to minus 10. Now we're going to build and test the circuit to see if it meets our design specifications. The op-amp chip we used in this circuit is 741. The red wire is connecting to the positive power, and dark wire to the negative power. The two green wires are both ground. Input resistor Ri and feedback resistor Rf. Input signal from the function generator and output signal connecting to the oscilloscope. To test the circuit, we first power it up using positive and negative 15 volts power supply. A function generator is used to generate the input signal, the sine wave. It's connecting to the input wire as shown before. Turn on the function generator and adjust the parameters. It's good engineering practice to double-check the circuit input. That's the input signal on the scope. Let's check out the output signal at the same time using another channel. It shows clearly the input and output waveforms have a phase difference of 180 degrees. This is introduced by the negative gain of the inverting amplifier. Remember, negative RF over RI. As for the amplitude, channel 1 is the input signal and channel 2 is the output signal. Recall our design specifications. We did use an inverting amplifier configuration, and the input signal was a sine wave with peak-to-peak amplitude approximately 1 volt. As for the circuit gain, we know both the amplitudes of the output and input, so we may calculate the circuit gain, which is defined as the output over input. The result is in the range of 10 plus minus 5%. So all of the design specifications are met.